Hello, everybody. So we need to start rather on time so that we will be able to finish on time. There will still be many, I guess, coming in the next few minutes. And please try not to stand near the door if you are chatting with someone. Just go down. This is not related to the session. Just go down, take a coffee or something and chat so that inside others can hear the talk. So welcome to the photon detection and photon detectors and particle ID session this afternoon. We have several talks, 5 in the first session and 3 in the second, plus review, and in between 16 posters. So you're welcome to visit presenters during the coffee breaks and also later. So we should start. The first presentation is by Daniel Guberman, and he will show us photo trap, kind of a light concentrator to increase the sensitive area of the silicon PM. So please start.
Okay. Thank you very much. Thank you for the introduction. Can you hear me well? Because I'm not a singer. I'm not very used to microphones. So, yeah. So today I will try to present an R&D project we are developing in PIsa at INFM, which basically aims at developing low cost and low noise large area silicon PM pixels. So let's see if this works. Okay, yeah. So during this talk, I will try to first start by introducing the motivation for developing PhotoTrap and introduce the concept of PhotoTrap itself, so that then I will present the prototypes we built and the laboratory measurements we made, and then discuss the performance we obtained, and if I arrive on time, which I hope so, just give a very, very brief overview of the applications in which I think a solution like this could have some impact, let's say. So basically, the idea of PhotoTrap tries to attack one of what I think is one of the main drawbacks of silicon PMs, which is the lack of large area silicon PM pixels. As many of you may know, silicon PMs are rarely commercially available in sizes larger than 6 by 6 millimeters square, and the reason is that basically capacitance and also darken rate increase with the area. This is a problem when you want to go for large experiments, or in general when you need to collect light over a large detection area, because if you need many silicon PMs, then your cost and the complexity of your readout increases significantly. One possible way to overcome this, and that has been explored, for instance, in high energy astrophysics, also in medical physics, consists on summing the output of several silicon PMs into a single one, so that this way you can somehow reduce the number of channels, achieving a larger pixel without a dramatic increase in the capacitance. But still this way you are increasing the darken rate, of course, capacitance still increases slightly, power consumption increases, and well, it has many other problems that in the end you also have some degradation of the signal to noise ratio, that for instance you lose the typical, this amazing single photoelectron resolution that silicon PM have. So here in PhotoTrap what we propose is a different approach, which is a low cost approach, let's say, to try to increase the sensitive area by a considerable fraction of the silicon PM pixel, but keeping the noise at a very low level, and if possible also the cost. And it essentially consists on a well-end shifter that is coupled to a silicon PM on the side, and now this well-end shifter will be surrounded by reflectors on the sides and on the bottom, and on the front part there is a dichroic filter which should have in principle very high transmittance in the absorption band of the well-end shifter and very high reflectivity in the re-emission band of the well-end shifter. So to see how it works, basically when a photon enters the well-end shifter, if it has the proper wavelength, and with the proper wavelength I mean the one of the absorption band of the well-end shifter, it will go through the filter, it will be absorbed, it will be re-emitted isotropically, and if we are lucky enough, this will bounce a little bit around, stay trapped inside the plastic, either by total internal reflection or by some reflections in the filter or in the reflective walls, until it eventually reaches the silicon PM. We will, of course, not always be so lucky. We will also lose many photons because it may happen that the photon escapes after some reflections, or that it is absorbed somewhere, even inside the same wavelength shifter, in the reflective materials, or anywhere else. Another important feature of this pixel, which sometimes may be a drawback, sometimes may be positive, is that it is only sensitive in the absorption band of the wavelength shifter. So photons at different wavelengths will either not go through the filter, but even if they go through, will very rarely reach the silicon PM, since they will not be absorbed by the wavelength shifter, and then they will leave away. So with this principle in the idea, what we have is a pixel that has an area that can be a few tens or even 100 times larger than the area of a single commercial silicon PM, but it has the noise, the capacitance, and the power consumption, and then essentially the single photoelectron resolution of a single commercial silicon PM, also at room temperature. And if we are lucky and we go for mass production, at some point we believe that the cost of this pixel will go down to the cost barely of a single silicon PM. Okay, so having said so, and having introduced the concept, let me just try to show you very briefly the developments we made for the proof of concept, where we built a few prototypes trying to test this solution. So to do so, we bought essentially commercial wavelength shifter plastics from Elchen. In this case, we are talking about wavelength shifters that are sensitive in the near UV band. Okay, this is the absorption band, this is in the dashed lines, and this is the re-emission band. These were 3 millimeter thick, and we bought them of different sizes, as I will show in the next slides. Its peak absorption is in the blue. It absorbs in the near UV, as I said. And we were lucky to find also a commercial filter that matches very well the spectral characteristics of the wavelength shifter. So it has very high transmittance in the absorption band, up to above 95%, above 320 nanometers, and very high reflectivity, so above 98% in the re-emission band of a wavelength shifter. As silicon PMs, we tried 2 solutions. One employing a single silicon PM of 3 by 3 millimeters, the other one in which we placed 4 of them in parallel, trying to get an array, let's say, which had the same area of a silicon PM of 6 by 6 millimeters, which, as I said, was the typically largest one you can find in the market. As a reflector, we just went for some reflective film, which is a diffuse reflector, which has a high enough reflectivity, let's say, although, as I will show later, the higher you go, since you will have many reflections, the better will be your efficiency. What you see here is some pictures of some of the prototypes we made. So this is the one of our pixels before adding the filter, because if we add the filter, as in this image, you don't see anything. Here we have in the middle the wavelength shifter. This is the diffuse reflector around. Also, you can see it on the bottom, and here we have an array of 4 silicon PMs connected in parallel. This is a 3D printed holder we made to hold everything together, and if you see from the side, you see it's also a very compact format with a very small PCB where we could place some commercial amplifiers just for the proof of concept. Okay. So we built 4 prototypes, and the difference between these prototypes lies on the area of the wavelength shifter it employs, since 2 of them are of 20 millimeters by 20 millimeters, and the other ones are of 40 millimeters by 40 millimeters, and on the type of silicon PM we use, the 3 millimeter version or the 3 by 12 millimeter version. So this, in the end, what changes is the ratio of the area of the wavelength shifter we are using to the ratio of the silicon PM it employs. So with these 4 prototypes, we perform a lot of laboratory measurements, and I will try to show the highlights of these measurements we did. Some very small comments on maybe on the simulations we perform with GM4. I'm not going to go into the detail because there is no time to do so, but I'm happy also to answer questions. So to do so, let me first introduce two important quantities in which we evaluate the sensitivity or the efficiency, let's say, of our pixels, which are the optical gain and the trapping efficiency. The optical gain is what we actually measure in the lab, because it's when we flash both photo trap and a silicon PM of the same area of the prototypes we are measuring with an homogeneous flux, let's say, we compare the number of photons that we detect with photo trap with the number of photons detected by the silicon PM. And this is what we call the optical gain, which in a different way would be how many silicon PMs like this would we need to get the same amount of signal we see with photo trap, okay? And what really quantifies somehow the efficiency of our pixel is what we call the trapping efficiency, which is the number of hits we have in the silicon PM per number of incident photons we have. So we take into account not only the photons that are absorbed and then escape, but also the photons that do not reach even the wavelength shifter in this case. So actually, as I said, what we measure is the optical gain, which is connected to the trapping efficiency by the ratio of the areas, essentially. Okay? So it's important not to confuse the trapping efficiency with the PDE. So the PDE of photo trap would be essentially the trapping efficiency times the PDE of the silicon PM it employs. So an ideal pixel would have 100% trapping efficiency and then a PDE equal to the silicon PM. So this is an example of one of the measurements we made for one prototype, which in this case, I forgot to put it, but it's basically the one of 20 millimeters by 20 millimeters with a 3 millimeter silicon PM. And what we see here is essentially how the optical gain we have in this axis, trapping efficiency in this one, how both increase once you start adding different components to the pixel. So these ones over here as what you would have if you only had the wavelength shifter without reflectors, without filter, so that basically you have a lot of photons that you are losing, how this increases when you add the reflector, and finally the addition of the filter. Okay, so in this case we reach a trapping efficiency of about 24%. I will show the values for all the prototypes in the next slide. But basically, this was important also to compare with the simulations we did in Giant, which is what I am trying to show with these dashed lines, what we expected from simulations. And it's important because there we can identify the relevance that the different parameters have in the efficiency of the pixel. And for instance, it is critical to have a very smaller gap between the wavelength shifter and the reflectors, or another very important item is the surface roughness of the plastics integrators, of the wavelength shifters. So this is basically the summary of the trapping efficiency we measured with all the pixels. So as you see here, we achieve the maximum optical gain when we have the maximum ratio of the areas, and on the other hand, the maximum trapping efficiency when the ratio of the areas is smaller. So in the end, depending on the application, you should go for a specific ratio of the areas. If you have space and your light is distributed over a very, very, very large surface, then you'd probably go to something where even if you can tolerate a lower efficiency, you can compensate with a larger detection area and then have an increased flux that you are detecting. I need to move a little bit faster, so let me show you this, which is basically a sort of sensitivity map of the pixel. So as you can guess, the silicon PM would be located here, and this would be the relative sensitivity all over the area of the pixels in with simulations and with the experiment, where of course with our rough setup, we don't have the same precision than in the simulation, but was more or less to show that we are getting close to what we are supposed to. And basically what we see is that the sensitivity is rather flat over a large part of the surface with a high sensitivity close to the silicon PM, essentially because of the solid angles that the wavelength shifting photons have that can directly reach the silicon PM without any bounces. While on these corners, this is the opposite case, and that is why we have the minimum sensitivity. This also means that if we could distribute silicon PMs all around the surface, then probably our sensitivity will increase. Finally, let me comment on the timing properties of the pixel, because as it was expected, the timing degrades with respect to that of a standard silicon PM, and the reason is, first of all, the time decay profile of the wavelength shifter, but especially the number of bounces that in the end determine the total track length that photons do inside the wavelength shifter. So when we combine the two of them, what we found is that the wavelength shifter gives an additional, let's say, degradation of the timing that in the end results in a time resolution of about 2 to 3 nanoseconds, which is, of course, not something you will want to use in high timing applications like PET, but it's still rather good for many other applications. Okay. Again, here, in principle, if you distribute the silicon PMs, also your timing performance would improve for the same reason than before. So, arrive at this point, this is the summary of the performance of our pixel compared to the standard photodetectors we have. Essentially, the message to get here is that if you can tolerate some degradation of the efficiency and the time resolution, in principle, you can build large area pixels with very low noise, very low capacitance, very low cost, and what I'm missing here, also very low power consumption per unit area. Yeah. Which is, and with this is what I want to finish, is very important in some applications. So because with these conditions, in which applications we can say we can use a pixel like this, I was mentioning all these cases in which you are facing a very large detection area, so that photons are spread over a large area. So even if you have a low PDE, you can increase your sensitivity just by increasing the area, which happens, for instance, in some experiments in Cherenkov light detection. One application I found could be very interesting would be in optical wireless communications, because there you are using LEDs, which have the light that are very spread, and you need compactness, you need low voltage, you need low power consumption, and so on. So at this point, I think I'm at the end. I have to finish. So this is the last slide where I can also thank the team, and I leave this slide for the questions and discussion.
Thank you for this interesting presentation. So, questions? Yes, please.
In your simulations, you seem to be hitting the levels right.
Yeah.
However, when you show the two-dimensional plots, they are off. So is this an accident?
No. Maybe I went too fast when I was trying to explaining. Essentially, in the simulation, we can simulate a very narrow beam exactly on a given position. While in our experiment, we are working with an LED, and then we have some spread in the light that makes that close to the border, which is where we have these main difficulties. It's very hard to really go into the position in which you can.
All right, so maybe a related question. How important were the qualities of or your understanding of the surface quality?
Well, that is precisely, that was one of the most important. I didn't have much time, and actually what I am showing here, these limits we found here, this corresponds to the best model we found that agreed better with this, which is a lookup table in Xi'an that was developed basically for polished crystals in positron emission tomography. And essentially, if you had a perfectly polished surface, this is a factor 2 better, at least. I mean, but when you go into a real surface, this is critical. Now, concerning what you can get in reality, we actually bought from Elchen pieces manufactured with different polishing techniques and also with different materials in PVT and PS. because we wanted to try specifically this, but at least with what they got us, we couldn't see any relevant difference from one to the other one.
So, another question, one quick one. We still have time.
Hi, I also introduce myself. I'm Laura Maninti from NYU Abu Dhabi.
Okay.
So I wanted to ask you, so first of all, what's the filter made of? Like, how do you make it? Is it something you deposit on top, or?
So we didn't make it to begin with. We bought it, and we were first trying to make it, but it is something that also for the requirements of the polishing is something that is hard to do in the lab by ourselves. So I know it is done by sputtering, magnetron sputtering, over a substrate of fused silica. But we didn't buy it. We didn't do
and the
it.
fact that you put several layers, it's because it's made of, it's like a stack. Huh?
Exactly. So in the end, this interference filter is just alternating thin layers of two materials, one of high refractive index, the other one of low refractive index.
And then the other one is where you had the experimental and simulation. If you can
Let
just
me see if I can go back. Experimental and simulations. I don't know which one. This one.
here.
Yeah.
Maybe I lost it, so I missed it. Like, what are the colors, like the 1.4 and?
Yeah. So it's the sensitivity compared to the sensitivity at the center. Okay. So it's the relative sensitivity compared to the sensitivity at the center of the pixel, which is where we get something flat. Let's say.
Thank you.
So just one quick question until we manage to make an online question. So can somebody bring the mic?
Can I do it?
Just a moment, yeah.
Okay.
Hi. I was wondering why not using 3D printed shapes like parabolics to focus and minimize the scattering on the board? Is it a problem of making reflective plane in a correct shape?
No, I mean, well, there are two things, no? There is in that case, what you need to manufacture with that shape is a Weyland shifter, right? This is what you need to do with that shape. So, of course, more weird shapes, let's say, are harder to manufacture and harder to polish to begin with, and then depends on the application of what you want. You can, of course, make a super concentrator, but then you lose compactness. Okay, so in the end, also, playing with geometry is something that you can do depending on the application.
Thank you.
Okay, so please, online question. Yeah.
Hi, Daniel.
Hi.
I would like to tell you that probably you don't know, but this is exactly the Xarapuca device that is the photon detection system of Dune experiment. You describe exactly the device I proposed in 2017. I can also give you some.
No. I
some
mean,
references. Yes.
I
can give you the reference.
I know very well Arapuca, of course. It's indeed a very similar technique. If I'm not wrong, you are not using a Weyland shifter plastic because you don't rely on total internal reflection, but on reflections on the reflectors and the filter, and it is used to capture the deep UV light from liquid argon, no? Right?
The Arapuca is in this way, but in 2007 we proposed the same device were shown
okay.
And the name is Arapuca, and we have 200 of these devices installed now in the experiment, and we already have information about efficiency, simulations, and everything. Probably you don't have this information, but they can send to you all.
I would love it, yeah.
Information.
Okay. Yeah.
Also about the filters you are using, the light guides you are using, we have a lot of experience on that. It's strange that you don't see this information.
Cool.
Okay, thank you for the comment. So we have to finish now and move on. Thank the speaker again. Our next speaker is Umberto Tamponi, and he will present the status and results of Bell particle ID systems.
Can you hear me, by the way? Yes, sounds like you can. Oh. Yes. Okay, excellent. So you already heard this morning in the first talk, I guess, about the status of Bell 2, how it's made, and what the prospects for the upgrade are. And you also learned that Bell 2 has some PID devices, PID-specific devices. In this talk, I will show you what's the status of them, well, how they are made, what's the status of them, and what we have to do to bring them to be fully functional, let's say. So I don't know how many of you are familiar with Bell 2. I don't want to start with a sketch of the detector. I would like rather to start with a sketch of the kinematics that we have to face that somehow influences the detector structure. So we collide the plus and minus at around 10.5 GeV to make an upsilon 4S that then decays into a BB bar pair because we want to study the B meson decays, basically. The main feature is that the collision is asymmetric, slightly asymmetric. Meaning that your kinematics will be slightly asymmetric, as you can see from here, where you have higher momenta in the forward direction, which is the direction which the boost is pointing, well, the other way around in this plot, and lower momenta in the backward direction. And also, this will mean that the detector itself is slightly asymmetric, not completely SLHCb, but not even fully symmetric. Okay, this is the infamous sketch of the detector, which is usually very complicated to see because it brings a lot of information. However, just to focus your attention a little bit, we have the interaction point here. All these brown things here are complicated focusing systems to actually achieve high luminosity. The high luminosity we were discussing this morning, basically. And then you have a silicon tracker in the middle, a tracking system, and then what we're interested in, which is the particle identification system in the barrel, which is Cherenkov-based, and the particle identification system in the forward part, which is also Cherenkov-based. After these detectors, you have an electromagnetic calorimeter, which will play a role in improving the performances of these guys somehow. And everything is embedded in the magnetic field, and then a return yoke, blah, blah, blah. Now, if you really, really want to be picky, actually every single subsystem contributes somehow to particle identification, because we have measurements of the d over dx from basically every single tracking system, except the inner pixels, which are not giving anything. And we have a measurement of the shower shapes in the calorimeter, which are now getting quite refined, so we can also do hadron identification with them, and then the muons. However, I will focus only on the Cherenkov parts of this, so on these two guys, which are called top and A-reach. Now, the coverage referred to the previous plot of these two systems is the orange one for the top, which is, let's say, the barrel one, goes to, in principle, infinity in momentum, and has a lower cut around here for the acceptance. And the A-reach is covering the forward part, which is not reached by top. I also highlighted here the region in which the d over dx information is actually dominating the PID determination. So you can basically see that except for this very little corner in the backward where we have very little acceptance, so we can pretend we don't care about that. We have coverage over the full phase space. Now, I mentioned that we have these two systems. They're both Cherenkov, but they work in very, very, very different ways. So the less traditional one is the top, which is a re-implementation of the idea of the Babar-Dirk, but looking at different quantity. So if you remember, the Babar-Dirk was basically was mostly measuring the image of the Cherenkov ring with the loose timing information, and the top is doing vice versa. We have a loose imaging of the ring, but a very precise measurement of the timing of the photon. And the trick is that if you just make a sketch of a particle crossing a Cherenkov radiator in which the Cherenkov light remains trapped, you can see that basically the length of the path of the photon depends on the Cherenkov angle itself. So if you measure the timing of the photon, and from that you infer how much length, how much time the photon spent inside the bar, you will have a measurement, an indirect measurement of the Cherenkov angle. So that's the principle. Implementing it, it's a little bit more complicated than that. However, in addition to these, you actually measure a second quantity, which is somehow completely entangled with this first one. Because the timing of the photons that you measure is not the timing from the moment in which the particle entered the bar, because you honestly have no idea about that time, you cannot measure it. It's the timing from the plus and minus collision at the interaction point. So actually it's the sum of the time of flight of the particle up to the system, and then the time spent by the photon in the bar. So it's a combination of time of flight and Cherenkov into a single system, basically. And this is why you have a nice coverage, both at low and high momenta. In addition to this, by the way, it also works as a threshold Cherenkov counter. So if you don't have light, well, you can infer what the particle species is from the location of the Cherenkov thresholds. The implementation of this system in Bell 2 is slightly different from the nominal one that you would find in seminal papers, mostly because of mechanical issues, let's say. So we have 16 bars arranged around the interaction point, roughly, I would say, 1.5 meters away from the interaction point. They are instrumented only on one side by microchannel plate photomultipliers because we want to be fast. And on the other side, you have a mirror, which helps you in compensating a little bit the chromatic dispersion by refocusing the light, which gets emitted in the forward direction and then has to travel back to the photomultiplier plane. Now, as you can guess from the description, the important bit of the top is the time resolution. It's a single photoelectron time resolution because we have order of 20 photons per particle crossing the bar, reaching the photomultipliers and being detected. So we want a resolution which is below 100 picoseconds from the readout only. So we have a combination of this specific model of a microchannel plate photomultiplier by Yamamatsu with a transient time spread of less than 40 picoseconds. It's not really easy to define exactly what the resolution is because the response PDF of the photomultiplier is not trivial. However, that's more or less the number. Readout by this chip developed by the Hawaii University with, let's say, 30 picoseconds of resolution. The combination of everything plus the readout, trigger, blah, 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 gives you something that is less than 100 picoseconds for most of the channels with a little tail of channels that have resolution higher than that. However, we are happy with that. We are within specification, let's say. Now, the A-reach works in the forward direction. And it's a completely different game. It's focused on providing PID for higher momentum particles and exploits, again, Cherenkov radiation, but with a different technique, which is the proximity focusing reach. So this is something pretty simple. You emit Cherenkov light in a radiator, and you have a detector plane behind the radiator itself, and you look at the size of the ring that you get projected onto this radiator. The problem here is that if you compute the formula for the resolution that you have on the Cherenkov angle, neglecting the parts related to tracking and multiple scattering, blah, blah, it boils down to this. So chromatic dispersion, it is what it is. The size of the pixel in the detector, and the so-called terms related to the radiator. Naively, the wider your radiator is, the broader this ring will be, and the worse your resolution will be. Okay? However, wide radiators also give you more photons, so you would like to have a wide radiator in order to have more photons and more resolution, but you would like to have a thin radiator in order to reduce as much as possible this term by having narrow rings. So the idea of the A-reach is to try to combine the two things into one by playing carefully with the refractive indexes of the radiators. So you split your radiator in two, and since you're using aerogel, you can fine-tune the refractive index to mostly whatever value you want. So if you choose your values wisely, you will have the ring emitted from the second radiator to overlap almost exactly with the ring emitted by the particle crossing the first radiator. So you will get twice the number of photons, but you would not degrade the resolution that you have on the ring. Basically, going from here to here, you replace, you add the factor divided by 2 in this term here. And if you do some toy Monte Carlo, indeed, this is what you get as function of the momentum. The Cherenkov angle has a resolution for a 4-centimeter radiator with single refractive index, which is more or less twice the resolution that you would have with a double radiator. So this idea is, as far as I know, something that was never tried before, and it actually works quite well. It was implemented in DA-Reach in this way. This is just a very awesome picture that I like because it shows the detector split in two. This distance in reality is 20 centimeters once everything is assembled. However, you see here the aerogel wall, and here you have the photodetector wall. This big gap in between is where you have to fit the cryogenics and the magnets for the final focus, so there's nothing you can do there. These are the specification of the two different parts. For the aerogel, it's this hydrophobic aerogel, I guess, produced in Japan, but I'm not completely sure with these specific refractive indexes. And for the photodetections, you have the HAPDs by Amamatsu with quantum efficiency around 30%. So what you want here is to have something that covers a lot of area with fine pixels, like 5 millimeter pixels more or less. And this is the device that's for you. More information on the DA-Reach, by the way, are shown in a poster that you can should definitely go and check out. However, how does this detector work? Now, if you really squint here, you would see an event display in which a track crosses the DA-Reach, and there is a very nice red ring here, which I definitely cannot see now, but believe me, it's there. And if you measure the angular resolution using BABAs, so high momentum electrons, beta equal 1, you get this PDF, this peak, let's say, that gives you a resolution of roughly 14 milliradians. So that's the number that you have to keep in mind if you want to compare the DA-Reach with other subdetectors. Now, how do they work? What's their impact, let's say? If you look at the regions of the top and DA-Reach acceptance, so mid-rapidity and forward, and you pretend you only have the d over dx, that's your separation power between pion and kaon. Now, there are a number of different variables you can look at when you try to put into numbers the PID performance. So I choose the pion to kaon misidentification rate. Basically, how likely is for my device to have a pion and call it kaon. As you can see from the d over dx only, this probability is very low at low momentum and then spikes when you cross the bands of the specific ionization. The performance that you have when you add the Cherenkov detectors is much, much better. By the way, these are data, and the pions are tagged from either D-star or K-shorts in this case. You see that you have this pretty classic feature in which your fake rate goes down in the region where you have less and less photons. Like, you have more and more photons and the momentum goes up, so your identification improves, then reaches a bottom here, which is basically your limit, and then goes up when this velocity starts increasing, and, well, all the rings start looking the same. You see that the fake rate that we reach with top is of the order of 5% in the region of interest, and order of 10% for the DA-Reach. Now, how this number compares with your expectation is what we're mostly working on at the moment. Basically, they don't yet match with what we were expecting from the Monte Carlo simulation for different reasons. You can see it here, that both in the case of the DA-Reach and the top, the fake rate that you observe is actually higher than the one that we were expecting from rather optimistic simulations, I would say. So let's start from the DA-Reach, because in this case we nailed down the origin of this discrepancy. And the reason is that you have cracks between the different tiles of aerogel. Okay? It's a region where you don't emit Cherenkov light by construction. And if you look at only at the tracks which are hitting the aerogel tile in the middle, so far away from the cracks, you see that, well, the PID improves a bit, as you would expect, but also the data and Monte Carlo the data and Monte Carlo lines go on top of each other. Telling you that what we have to fight against in this case is a precise alignment of where these tiles are, which is really what's dominating the discrepancy between data and Monte Carlo here. In the case of the top, the situation is way more tricky, I would say, because we weren't really able yet to nail down a single source of discrepancy between data and Monte Carlo. We ruled out a number of things, like, for example, we know that the discrepancy doesn't come from the point in which your track enters the bar. We know that doesn't really come from how many photons you have, because that quantity is rather well described. However, we discovered that if we employ a much better simulation of the beam backgrounds by using, instead of simulated backgrounds, what we actually record from data, we recover half of this discrepancy. In this plot, you have basically the fake rate in the top as a function of time in different experiments. And the blue line is the naive expectation. The orange points are the better Monte Carlo, and the black points are the data. So this is telling you that what's dominating the discrepancy between data and Monte Carlo in the top case is actually our capability of describing correctly the beam backgrounds. There is still a residual discrepancy that we have some ideas about, but we're still working on it, so I won't really talk publicly about that at this point. Now, the last lesson that we learned is that we have significant degradation in the particle identification by multiple scattering and decays in flight. Basically, what happens is that our devices are not looking for the rings and then trying to match the ring with something, but they are looking at where the track is extrapolated from tracking and look if there is a ring or some photons associated to it. So if your track has decayed in flight because it was a kaon, or has hard scattered in the material in front of the reach because of reasons, it still gets extrapolated into your device, but in a point in a region where you don't actually see any photon because nothing entered the device there. And this is pretty dramatic in the case of a reach, because the reach is located behind the electronics of the, sorry, not the electronics, the cabling of the inner tracking system, and you can actually see, even if you plot the number of Cherenkov photons associated to the tracks that you see in the reach, that you have regions very nicely reproducing where the cables are, in which you have less photons. So a lot of material in front of the reach is giving you these troubles. What you would like to have, of course, is a tracking plane behind your system that is able to tell you if the track actually passed through the Cherenkov detector or not. We don't have it, but we can rely on the calorimeter, which can tell you if there is an ECL cluster associated to the track behind the system. So if you require, for example, your track to have a cluster behind the A-reach, suddenly your performance go from the gray line down to the black line, and also data in Monte Carlo overlap very well. Telling you that basically if you want to construct such a device and you want to be wise, place a tracking plane behind your system because it will really, really help you. Okay, these are my conclusions. I will just leave them here. Just to say, A-reach and top work, I would say well, despite being new systems tested for the first time. We still have to fine-tune something, but we have a very long shutdown ahead of us to accomplish it. Okay, thank you.
Thank you. Thank you for this nice review of Bell 2 for particle ID. Question, please. Okay. We will get back on track. Aha, sorry, there is one.
Remind me, what is the best timing resolution that you have?
In top, the best photoelectron timing resolution is, let's say, 80 picosecond measured with the laser. Then if you want the resolution that we have from the Cherenkov photons, you have to include chromatic dispersion and the thickness of the bar, and you go around 200 picoseconds.
And your silicon PM has a quartz window? Or?
No, our microchannel plate have a glass window.
A glass window?
Yes, we have also a wavelength shifter in front of the glass.
But you don't see any...
No, because the photomultipliers are actually mostly outside of the acceptance. Oh. So it's very rare for a track to enter them. They mostly enter the bar, and then you get the photon from there.
Okay, if there are no more questions, let's take the speaker again and move on. Our next speaker is Nicolo Vladivesus, and he will talk about development of a hybrid single photon detector with pixelated anode. It's a combination basically of MCP PMT and CMOS sensor inside. Yeah.
Yeah,
Okay.
exactly. So yeah, I was going for sorry, where is the? There. Okay. I was going for a long title. Yeah, so a hybrid detector. I will talk you about the detector that we are starting to design in Ferrara. And basically we'll talk about the hybrid detector concept, and I will show you how the Timex4 ASIC is integrated in this detector. I will talk you briefly about the expected performances, because we don't have much yet, and I will then go to the design status and a brief update on where we are. So the hybrid detector was proposed by Massimiliano Fiorini, and it won an ERC, so we basically founded using an ERC. We are trying to develop a single photon detector based on a vacuum tube with a transmission photocathode with high quantum efficiency photocathode. And basically, this tube integrates a dual microchannel plate stack, and the readout is done using a CMOS anode that integrates basically the front-end electronics. So basically, it acquires the signal, digitizes it, and then send it out as basically a digital signal. This detector will have timing resolution, so time of arrival and time over threshold resolution of few tenths of picoseconds, a position resolution of 10 to 5 to 10 microns. Maximum rate is basically given by the ASICs is 10 to the 9 hits per second over the 7 square centimeter area of the detector. And we expect a low dark count rate, so 100 counts per second. And of course, here you basically have the number of channels divided by the area of the ASICs, and is 0.23 mega channels. So here is a sketch of the detector we are trying to build. So as you can see, there is a vacuum tube. In this vacuum tube is closed on the top side by this quartz window with a photocathode. Then you have the MCP stack that basically is used to multiplicate the photoelectrons produced on the photocathode, and then the silicon of the CMOS anode is on the bottom and is wire bonded to a ceramic carrier. All the signal are basically carried out of the detector using a PGA and a proper a custom socket, basically. The idea here is that all these detectors, this assembly will be built in order to minimize distances between the photocathode and the MCPs, and the MCPs and the pixelated anode. So that basically you use what is called proximity focusing. So basically you have a small area interested by each event. The readout is used using high-speed connection. I will talk you a little bit more about these later during the talk. And of course, as you can see here, since you have an integrated electronic, you need to cool it down, and to cool it down properly. So you have also its sink and what else that we are also trying to develop together with this detector. So starting with the top, let's say, the photocathode, really here we are planning to use whatever the industry is able to provide. We are trying to go for example, bialkali photocathodes that have high quantum efficiency of the order of 50%. And basically, if this photocathode is good enough and is cooled enough, this will give you basically a low dark count rate. Of course, since here you can use whatever photocathode the industry is able to give, so the design is flexible enough to allow for different photocathodes. Below the photocathodes, we have the MCP stack, basically two MCPs in microchannel plates in a chevron arrangement. The pore size we are going to is 5 to 10 micrometers pore size. And we, again, based on what the industry is able to provide, and we plan to have an atomic layer deposition to increase the lifetime. So we plan to use this device in low gain and with a atomic layer deposition in order to have to be able to reach an integrated anode charge of 20 coulomb per square centimeter. And again, here we are trying to minimize distances in order to have good resolution on the position. Below everything, you will have an electron cloud that is read out directly by the pixelated anode. Of course, you will have the cloud will spread over a number of pixels, so you will have clusters, and this is quite important, as you will see later. And then you will have this pixelated anode that integrates the analog and digital front end. So you will have basically as output pixel coordinates, time of arrival, and time over threshold. And the output is basically words of the 64 bits with the 64B, 66B encoding transmitted of 16 high-speed links and at 10 gigabits per second. So the ASIC that we are planning to use is the Timepix4. The Timepix4 is a 65 nanometer CMOS ASIC. Currently, we are at V2, which should be the final prototype, so basically the production. That is basically being produced at the end of last year, and this is currently under test at CERN at other institutes. So here you have a sketch of what the Timepix does for each pixel. So basically, this is okay. You have your pixel. The charge is basically integrated and amplified. Then you have a discriminator that sets a threshold, and you have here you will basically have a digital signal, and then you measure the time of arrival and time over threshold for each signal, and then you basically have a router and other electronics in order to be able to read out your chip. These ASICs uses a matrix of pixel with square pitch of 55 micrometers, and as you can see here, naively you would expect the resolution of being of the order of 10 micrometers or so, but really you can go a little bit lower using cluster. And again, same story for the time to digital converter. The time to digital converter that is implemented in the ASICs uses 195 picosecond bins. So the naive resolution here should be 56 picosecond, but again, you can improve on that. And here again, you will have a very high data rate capability. So basically here, depending on the MCP that you're using, you're either limited by basically the MCP and the ASIC have similar maximum rates. So I told you that you can really improve on the resolution. How can you improve on the resolution? To improve the resolution, basically you start with the output data of your ASICs. That is basically the time of arrival and the time of threshold. But of course, you will have time walk effects. And but since you have both the time of arrival and the time of threshold, you can correct for that. Nothing new on this. And then you can start performing 3D clustering. With the 3D clustering, I mean that you can cluster both in the space coordinates, so in X and Y, and you can also cluster in time. And by doing this, you can have basically an average time of arrival of your cluster, and this can give you a better time resolution, and you can go down to a few tenths of picoseconds from the 55 picoseconds that you expect for single pixel events. Again, second version of the time PIXA is available. Currently, we are studying the performance of this ASIC, and we are starting to test it. So we don't really have the photocathode and the MCP, but we only have the silicon anode, and we are starting to design the control software and the control firmware for the detector. Furthermore, we are starting to study the ceramic carrier the ceramic carrier performances. These are quite critical because here ceramic is not really a good material to have PCBs with the high-speed links, and PGAs are suboptimal for high-speed links. So we are planning to have prototypes for these and to study really the performance of signal integrity on this kind of devices. And plus, since we want to have very narrow tolerances on the distances between the photocathode and the MCP and the MCP and the anode. Again, we are also studying the mechanical tolerances for this device. So here you can see basically a very brief report of the TimePix4 test that we are performing. So these are basically very preliminary measurements. First of all, as I told you, we need to cool down our detector, so we need to define cooling requirements. To have cooling requirements, we really need to measure the peak power of the ASIC, which is the biggest thing, the highest source of heat inside our detector. And as you can see here, we have multiple power rails, and we have in real data taking. So this basically square shape is the high level is the real data taking. We have basically 3 watts, so 2 plus 1 watt dissipated over the 7 centimeter of the ASIC, and we need to design a proper cooling apparatus to cool down the detector. We are also studying equalization procedures because, as you can expect, each pixel needs to be equalized independently from all the others, and so again you have lots of parameters that you can play with. Here basically you have the Gaussian that is given by the equalization with different DAC, so digital to analog converters to set the threshold for each pixel as basically an example plot. And we are also preparing calibration procedures and parameter optimization for the TimePix. As I told you before, we are also testing ceramics. This is an older version of an existing ceramic with the PGA pin that we are using for testing. So for example, we can do electrical tests by simply injecting signals in these pins and basically making what is called a loop back and reading back the signal. And so we have first qualitative electrical measurement on an existing device, and we have simulation. An example of the simulation is here. You can simulate pins, you can simulate PCBs and stuff like that. And what is interesting on an electrical point of view is that what is really the limiting factor is the ceramic itself, is not the PGA pin. Typically, here you expect the pins to have a bad S parameter, so basically this is the transmitted signal, but is not really that bad. But what here really the limiting factor is the ceramic and the parasitic capacitance on the aluminum oxide. We are also creating a software and a full DAQ system. So here, so basically we have our first tests were done with an existing DAQ system for the TimePix4 which was produced by Nikef, which is a great tool for preliminary test, but is not fully open software, open firmware, and open hardware, so we cannot use this for the final test. So we are designing our system, and you can see here that we are designing something starting from a development kit, plus some kind of adapter that we designed to be able to send the correct signals to our detector. We have a sketch of the firmware, we have a sketch of the software, and we are starting to build a full system to be able to use this detector. So in summary, we are developing a detector for visible single photons based on a vacuum tube with a bare Timepics4 CMOS ASIC as an anode, and using a dual microchannel plate stack for multiplication. This detector will allow the detection of up to 10 to the 9 photons per second with the simultaneous measurement of time of arrival and time of threshold plus deposition, exploiting both the timing and position resolution of the MCPs and the Timepics4 ASIC. The detector will be produced together with the full DAQ, with the full DAQ system, so that end user will be able to directly use our detector. Development is still ongoing, and we hope to be here in a couple of years to give you better news. So thank you for your attention, and thank you for the Photon team for their great effort in developing this system.
Thanks. On the time of correction, so the rise time you expect, I guess, in time peaks is several nanoseconds, 5 to 10, and then you have to correct that to 10 picoseconds. So,
well, the rise time here really is determined by the MCP signal alone, because you basically use the metal pads on the time peaks for the anode, right? So the capacitance there will be small enough to be negligible. So basically here you have this is the bare time peaks for ASIC. So you have a pad which is like I don't remember the number. I think it's something like 20 micrometers of radius. Is like a round pad. So really here the rise time is given by the creation of your signal and by the MCP. We expect.
The preamp contributes. I mean, at some point the speed of the time peaks is I don't know, 80 megahertz, something like that. No.
Well, but that is the time that time is given by the digitization part, right? So it's basically given by the TDC that is giving you the limit is on the digital part, not on the analog one, right?
Well, I'm not sure. In the time of correction.
You can continue probably later. So, or there, if you can.
A very interesting design indeed. To which extent is it sustainable to magnetic field?
We really don't have any study on that, so I cannot really comment on that. But yeah,
I guess it is supposed to be placed in magnetic field.
Yes, it can. We expect to be able to place it in magnetic fields. We will need to have proper. Again, this is really the design right now is. Limited, but what the industry can give us, because for example here we can you want better performances under magnetic field, you can choose the material here, you can like shield it and stuff like that, but really right now we are just basically conducting an industry, telling what can you provide, what can you have on the shelf that we can use to integrate this thing. And we are not really caring about specific performances in in specific environments, right?
Okay, good luck, thanks.
Maybe here? Sorry, probably miss it, but what are the potentials between cathode microchannel plate and channel plate and chip?
So
and then if you, sorry, maybe a second part, could you elaborate a little on the spread of the charge with respect to the anodes of the pads of the chip that collect? So I guess the pads do not cover the full area of the chip, so you guys have to spread out the charge on a few pads.
Okay, so here you have kilovolts, and this is really here. What the distance here is limited by the presence of the it is I think is to with the design voltage is 2 kilovolts. Difference between the pads and basically the anode and the MCP stack. The distance here is limited by these wire bonding cables, wire bonds. Basically, here you have 100 micrometers at least for the wire bonds plus whatever distance you need to have proper insulation on these. And again, here you have one. Okay, so this is regarding the voltages. And sorry, the second part was about the spread. So really the spread, again, the target is to have 200 microns here, and you expect you expect this electron cloud to be spread out over few pixels, so group of like 4 pixels, something like that. But again, since we don't have really a value at the moment for this distance, we are not able to have a good estimate on the spread of the electron cloud. Once we have a good estimation of this distance, we will run simulations again and yeah.
Okay. One quick question, and then we will. Oh, I'm sorry, we'll need to move on. So.
Presumably the lifetime of the device in the sense of integrated charge is determined by the microchannel plate?
Yeah, basically yes. So the life of the device.
How many coulombs at the anode before it dies?
So basically we have this estimate of what is it? Of these 20 coulomb per square centimeter, which is something which is reasonable. Again, this is limited by the microchannel plate that you use and by the gain of the microchannel plate stack, right? But we plan to have something like this, and this is kind of a strong limiting factor for these kind of devices because performances will degrade a lot.
We need to finish here, I'm sorry. My mic is not working again. So let's thank the speaker again. And he will tell us about the capacitively coupled LAPPD, a large area MCPP and D, coupled with different patterns readout capacity.
Good afternoon, everybody. I hope you can hear me. The title is even longer than in the previous talk, but what it is all about is about making LAPPDs usable for ring imaging Cherenkov applications or any other applications which would require fine pixelation. So the LAPPDs have been around for a while, and the MCP-PMT concept was introduced in the previous talk, so I can probably skip a portion of this material. So the LAPPD is basically a large MCP-PMT, and they are available from Incom in 2 different flavors. So basically generation 1 and generation 2, where generation 1 is a strip-line internal anode, so you get a device 20 by 20 centimeters with 28 strips in it. Generation 2, as it is shipped, does not have internal structure at all, so the tile itself is pretty much uniform, and it is shipped with an 8 by 8 pixels pad. So the game changer here, of course, is that you are not obliged to use this particular pixelated board, so you can use whatever board you want to design. And even that none of these 2 varieties is directly usable for ink imaging Cherenkov detectors, so by modifying this readout plane, one can hope to come up with something which has appropriate pixelation. So all in all, these Gen 2 LAPPDs can be purchased in either 20 by 20 centimeter or 10 by 10 form factor. So they are expected to be very cost efficient in mass production, reasonably high quantum efficiency, low noise, and uniform enough and high gain. And single photon timing resolution is preserved on the level of 50 picoseconds, if not better. So, but as I said, so they don't exist in finely pixelated configurations, and the talk will be basically devoted to this. Clustering was mentioned briefly in the previous talk already. I still want to spend a minute here, because when people design their readout planes, they keep thinking about the picture which you see on the left-hand side of this slide, where a single photon generates a single hit in one of the pixels. And spatial resolution, of course, in this case is driven by pitch over square root 12, because the information of where inside the footprint of a particular pixel photon hit it is lost. You get a device with manufacturer-defined pixelation, and this is not what Gen 2 LAPPD is about. So in this case, one photon produces a multi-pixel cluster. Pixelation is user-defined. So in this particular case, you can see 8 by 8 matrix with 3 millimeter pixels. And RMS for this generation of tiles is 3.5 millimeter. And spatial resolution can be times better than square root 12. So as long as occupancy is not an issue, so one can crank up signal-to-noise ratio by using, for example, low noise, high frequency preamplifiers, and get resolution of maybe a few hundred microns out of pretty large pixels. So this is the focus of my talk. So Gen 2 pixelation via custom readout board design. I start with the lab measurements at Brookhaven. So on the left-hand side, you can see a picture of very basic equipment which we have in the lab for this particular studies. So in the rear, you see LAPPD with the characteristic X shape spacer. So then 3D translation stages, fiber with the laser signal and very simple focusing optics. So it's pretty easy to get size of the spot below 100 microns. We tried various type of pixelations. So for this stage of LAPPD technology, these complications make no sense, actually. So one can get pretty much the same result with square pixels because the charge spread is pretty large. But it can be different for the next generation, where all the gaps in the stack will be minimized, and hopefully the charge spread will be actually much smaller. So my next slide. So this is the rear side. So the LAPPD is sitting behind this PCB. So the PCB is custom made. These are the adapters from high-density connectors into MCX cables and then to the digitizers. These are conventional V1742, and we have 320 channels. The setup is modular, so it's probably not really convenient for any final installation, but for tests, I can assure you that to disassemble this thing, disconnect all the patch cables and replace the board takes like half an hour. The first concern was a crosstalk on this configuration with capacitively coupled LAPPDs. And it turned out that by building the internal stack of the board in a proper way, one can definitely reduce this crosstalk to percent level. So what is shown here is a direct measurement where you inject signal, square pulse in 1 pixel. So you check induced signal on the neighbor pixel, and it's 10 out of 500 millivolts. On this picture, you can see a different representation. So these are the waveforms where the laser spot was somewhere here. So the signal amplitude is like 10 to 12 millivolts. It is a 5 by 6 pixel area, as you can see, and 50 nanosecond window, time window. The traces are oriented vertically in this picture, and in some sense you can see some crosstalk vertically, which is not present in far neighbor pixels horizontally, but it's pretty much bearable, I would say. So now the measurements with 3 millimeter square pixels. So this was tile 97 with thin ceramic base. So we have a board with just 8 by 8 pixels. And if you make a linearity scan across 1 pixel, so you can see that the response of this simple clustering procedure is pretty linear. And once you move the laser, so basically this cluster is moving across the pixelated area, and the width in one spot is something like half a millimeter. So it's already better actually than the square, than the 3 millimeters over square root 12. So one can try out more complicated pixel layouts. So you can see here 2 pixels, the red one, so this is a single pixel which samples in horizontal direction. So this is a single pixel which samples in vertical direction. And doing the same scan, so this idea actually comes from MPGD studies in the EIC R&D program. So one can see that resolutions below a millimeter, given signal-to-noise ratio, which we had, are pretty achievable. And the important part is the sentence below, so that as long as occupancy is acceptable, it's kind of obvious that you can stack these pixels vertically and will not lose the spatial resolution, but can decrease by substantial factor of the number of instrumented channels, if this is of a concern. So now the beam test at Fermilab in June last year. So this was a joint venture of BNL, Incom, Argonne, Georgia State, Stony Brook, and a couple of other groups. So we basically brought our setup to FTBF beamline, the primary beam. So we used in this case a spheric lens as a Cherenkov source, and I know that other people do it differently, so the advantages of this setup are listed here. So you get an off-the-shelf component which is very well controlled, so you don't need to do any modifications, and it gives you a very crisp ring of known diameter, which just basically follows from the simulation. So the protons go from left to right, so then get reflected and hit the LAPPD photocathode. So the pixelation which we used is shown here. So again, the board is custom. You can design it in whatever way you want. And what you see here is a clear rim, which are clusters of the single photons. And if one makes a cross-cut, one can see that one radiator is out, so you basically see some background. So once radiator is in, it's a clear signal, and the width is 600 microns. In that case, I remind you, there were 4 millimeter pixels. And this is your single event, which is not the best one. And ideally, we would like to see clear clusters here. But in principle, this is what you expect as a typical event. So yes, one can measure single Cherenkov photons with sub-millimeter spatial resolution using these LAPPDs. I'm coming to my extended summary. So the first part is basically the actual summary of what I just showed. So we provided proof of principle measurements confirming feasibility of these LAPPDs for single photon detection in Cherenkov imaging applications. This is the first shot, but it looks feasible. So then we tried out several ideas for the readout board optimization, and there's plenty of stuff to do. So one can further optimize the readout board, onboard electronics integration is a question. So then the practical applications, I will show this in the two last slides. The interesting connection is positron emission tomography, where high-performance photosensors can be the actual game changer in the technology. So our next beam test campaign is next month. So what we are going to do next time is to extend the basic setup, so which was this part. So there will be a reference tracker, the GEM tracker. So we will try two other configurations with direct demonstration of aerogel-based Cherenkov performance. So we are getting new LAPPDs from Incom. So they have 10-micron pores. The window material is UV quartz. The tile is being sealed now, and we expect at end of May at BNL. So unfortunately, the timing is such that the beam test will be first and then the lab measurements. But as Sylvia pointed out, the EIC timelines are such that we cannot allow ourselves to lose a year of beam tests, 1 year cycle. And maybe, just maybe, we will be getting HRPPD as well, so which is a 10 centimeter flavor of beam. This is almost the last slide. So these are the readout boards which we are going to use. And back to the questions, to one of the questions which was asked before. So the pixelation is such that there will be a group of pixels in the middle of the circular pattern to see the direct photons produced in this UV quartz. So we expect like 100 photoelectrons given the quantum efficiency and the thickness of the material. And the idea is that we want to demonstrate simultaneous ring imaging and time-of-flight performance in the same setup, because this is one of the configurations which is proposed for EIC in particular. And this is my last slide, just an advertisement. So we are now doing the LAPPD workshop series, which is organized by Argonne, Brookhaven, and INFN. So I mentioned in one of the previous slides that INFN is also joining the beam test campaign in June. So you can see that this is the agenda of the first meeting, so where there were reports from the research groups across the world, and then the manufacturer talks and ASIC manufacturer talks. So we plan that these workshops will be regular, 3-4 per year. And if people think that there are topics which can be incorporated in the agenda of the next one, please, you are more than welcome. Thank you.
Thank you for this nice presentation. Questions? Uh-huh.
Can you say a word on the timing performance that you expect?
Timing is a little bit of a pain, so we were expected, you mean that the timing resolution? Yeah. We had issues with DAQ synchronization in the first beam test, but you saw in the setup so that we are planning to have two reference planarcons. So in fact, it can be that with this new generation of LAPPDs, the timing resolution for, it's not single photon, of course. So it's like, as I said, like 100 photons in a blob. So it can be that the timing resolution will be even better than the resolution of a reference planarcon, and it could be tricky to subtract it with just a single reference device. So I would be very much surprised if it's not going towards 10 picoseconds. So as you know, we are using DRS4, which requires tedious calibration to get there. We are getting there, and hopefully there will be something to show in Bologna in July.
If there are no more questions, let's thank the speaker again. next speaker is Stefano Fesanti, and he will talk about the DSSC soft X-ray detector. So, please start.
Okay. Thank you for the introduction, and good afternoon to everybody. I present this on behalf of the DSSC collaboration. And first of all, DSSC stands for Depth First Sensor with Signal Compression, which is a megapixel camera designed for the soft X-ray in the energy range between 250 eV to 6 keV, and it has to cope with the bunch structure of the European XFEL, where up to 2,700 X-ray pulses separated by 220 nanoseconds are pulsed every 100 milliseconds. The camera, the first megapixel camera, features miniaturized simulcron drift detectors, and the second camera will use instead depth sensors. The readout is a full parallel readout with a in-pixel analog to digital conversion and an in-pixel memory of 800 frames with the possibility to overwrite the non-interesting events to reach up to 2,700 pulses. And the output data rate is up to 134 gigabit per second. The camera aims to have a dynamic range of up to 10,000 photons at 1 keV, and we want to have also single photon resolution. So this is the overview of the system. Basically, the camera is divided in 4 quadrants, and each quadrant is divided in 4 modules called ladder. The ladder is the smallest independent unit of the camera that can be operated alone, and it's composed by a focal plane module that comprises 2 sensors and 16 readout ASICs. The ladder electronics is composed by 4 regulator boards that can power separately all the ASICs and the sensor, and an input-output board that is able to give the time signals to the focal plane modules and read out the data of the 16 ASICs. It operates in vacuum, and the optimum temperature for the mini SDD is -20 degrees, but also room temperature is possible. So the camera uses very low power, so the total power dissipation is only 263 watts. This is possible thanks to the so-called power cycling. So we switch on all the ASIC powers only during the data taking, and we switch off the unneeded powers for during the data readout, so that we can achieve a coolant load in vacuum of 150 watts, which is 142 microwatts per pixel. And this is in agreement with our expectation and the simulations. Now, the first camera uses mini SDD sensors with 2 drift rings and with a hexagonal pixel shape. It's each sensor is 128 by 256 pixels, and each anode is mounted to the correspective pixel in the ASIC, which has a charge-sensitive amplifier inside. And in this case of the mini SDD sensor, the system is linear, and the energy and dynamic range are given by the gain of the ASIC and the ADC resolution. So this is the full format ASIC. It can read out 64 by 64 pixels, and it contains both the depth and the mini SDD front end. As I said, the mini SDD front end is a charge-sensitive amplifier. Then we have a trapezoidal filter with a flip capacitor to generate the trapezoidal filtering function. And then we have a 9-bit single-slope Wilkinson ADC. The data is stored then in 800 memory cells, which resides in the pixel. We have a lot of bits to control the coarse gain, and 6 bits to control also the fine gain trimming, so that we can have a nominal accuracy of 2%, And we also have 4 bits for the offset trimming, and I show now why we need all these bits. So we need the coarse gain trimming to operate with photons of different energies and to define the input dynamic range associating a defined number of photons into a single ADU. This because we have only 8 bit at 4.5 megahertz or 9 bit at 2.25 and lower frequencies, and we need to have our single photon sensitivity or maximize the dynamic range. With the fine gain trimming, we can equalize the gain dispersion over the matrix, and we can then assign a precise number of photons per ADU. And in this sense, we also need to make an offset trimming in order to place the first photon in the middle of one ADU so that we can minimize the error count rate. From these plots, you can see that we have overlapping gains for the coarse gain settings, and we can finally have a granularity considering both the coarse gain setting and the fine gain settings. We have a granularity of the gain of 1% that allows us to define precisely the gain for any arbitrary energy between 0.5 kV to 10 kV. So these are the result of the first megapixel camera that is already in operation. This is a dark image, and we have a failure rate of 3 ASIC out of 256. So it's less than 2% of the active area concerned. And the camera has been calibrated using a pulsed X-ray source at the European XFEL. And we can see that we have a good uniformity along the 16 modules. And we achieved an untrimmed gain of about 400 dB per ADU in the standard configuration with a noise of about 58 electrons RMS. And also with a dispersion of 1% and 4.5% respectively. The camera has been installed in May 2019 at the Spectroscopy and Querient Scattering Instrument at the European XFEL, and the first user experiment was in May 28. Since then, and up to December of last year, 16 experiments have been performed despite the COVID situation, and this year 4 more experiments at SES are foreseen for the first semester. And in the meanwhile, the DSSC camera has also been commissioned in the other instrument for the soft X-ray at the European XFEL, the small quantum system, for performing 1 experiment. So now, towards the depth-fed camera, the second camera will be equipped with depth-fed arrays. The depth-fed will allow us to have low noise for photo resolution and also the high dynamic range which is required in some of these experiments. The pixel array are compatible with the camera, so the electronics is fully compatible with both mini STD and depth-fed arrays, and we can have a non-linear gain response of the pixel. This is an active pixel sensor. It's basically made of 2 transistors. The gain transistor has underneath the gate a deep implant so that we have a potential minimum for the electrons that can will alter the current of the transistor, and this is the amplifying stage. And moreover, by shaping this deep implantation, we can make the nonlinear range so that for the few photons, for the few electrons that are collected, the implantation is only underneath the gate so that you achieve the maximum gain, and you can make more implantation that overflow under the source so that the sensitivity of the transistor is less with the higher collected charge. So these are the first results of the depth-fed ladder prototype. We managed to made it fully working with a 100 microamp per pixel with depth at bias current. This means that we have 1.3 to 1.4 nanoamps per electrons of gain, and with a integration time of 15 nanoseconds to compare with the mini SD camera, we reached the equivalent noise charge of 20.72 electrons RMS and a gain of 200 eV per ADU. Moreover, we try to explore what are the limits of the system, and with using an integration time of 300 nanoseconds at 1.1 megahertz, we achieved a noise of 9.8 electrons RMS on average in the matrix, and this at near room temperature conditions. So the ladder was kept fixed at 18 degrees. And here you can see the map at 2.25 megahertz with a 20 electrons noise and a representative iron 55 spectrum in the bottom part. Moreover, we tried in the lab to see the compression curve of the depth. Unfortunately, we have been requested to have 150 nanometer of aluminum layer on the backside to block the light. So it's not in our lab it's not easy to see the nonlinear curve by using the light. Nevertheless, we use a laser pulsar with diffusing the light on almost one ASIC area at a single time, and we integrated the charge into the depth internal gate without clearing it, and we acquired 400 LED pulse reading after each charge deposition, the charge value in single integration mode. And with this, we can scan all the curve, and you can see these are the overlapping curves of almost 63,000 pixels. And we also try to estimate what is, or measure, we measured what is the position of the first gain change of the depth, which is 80.6 keV plus minus 5.4, which means that we have a dispersion of 7% roughly, with a gain in this case in the linear range was 473 EV per ADU. That means that we can achieve more than 1,000 photon in this configuration in this case. So from these curves we can estimate the dynamic range with 8-bit. This is the worst case considering the 4.5 megahertz operation, and we can achieve 1,000 photon at 500 eV per ADU, and more, or roughly 9,000 photon at 1 kV per ADU. We also used the first prototype at the beamline. The aim is to perform the full characterization of the sensor with a real speed of 2.25 megahertz. And we use the fluorescence of the aluminum, and you can see here in the spectrum that you can really see distinguish the single photons, and we have a signal to noise ratio of about 30. That means that we have roughly 14.1 electrons RMS of noise. And this is my last slide. So the first 5 megahertz 1 megapixel camera has been completed and is successfully used for the experiments. And despite the COVID, we have reached already 16 experiments with 2 papers published on high-ranked journals. And the second camera will be based on CMOS depth active pixel sensor that will allow both single photon sensitivity and high dynamic range. And this camera will be available at the end of this year. The first operation of a CMOS depth ladder confers the excellent performances that are expected from this technology. We have 3 times better noise with respect to the mini SDD and 30 times better dynamic range at 1 kV photons. And yeah, we have as low, the lowest noise measured at the moment is 9.8 RMS at 1.1 megahertz on average on the full camera. So thank you.
Thank you for this presentation. Time for questions. Yes, please.
Going back to the depth FET, I see that the linearity in the first gain stage is actually quite good, but
yes.
the linearity in the other stages is a bit, yeah, not optimal. Is it a problem for calibration? How does it work?
No, actually we can scan the characteristic, and we also can model mathematically, so it's not a problem to fit the curve,
so
and we do it for all the pixels. So we have to measure. Yeah.
Okay.
Yes.
Thank you.
Okay. Another one.
Hi, Henry Roberts from NYU Abu Dhabi. I was just going to ask, can you give us a sense of what the energy resolution is for the mini SDDs?
It's 58 electrons.
Okay. And what
at 400
is
dV per
means
radian.
by which they're cooled? Is it pellet
Sorry?
cells? And what is the means by which they are cooled? Are they
to reduce the
LTA
leakage
cells?
current? Yeah.
But how? Sorry.
Sorry?
How are they cooled? Like
So if we can go back to the slides, so we have these are the copper blocks, and it's cooled with silicon oil to minus 20 degrees.
Thank you very much.
So the focal plane modules is tightly connected to the copper block to achieve the best cooling possible. Yeah.
Thank you.
Okay, I don't see any more questions, so we came to the end of this session. Let's thank all the speakers again of this session. Sorry? Yeah, we will convene in 20 minutes, basically, so 17:30. And now you can also visit the poster site. Okay, so we should continue with our session on photodetectors and particle ID. The next speaker is Matteo Morocci, and he will talk about the calibration and performance of assessment of the TOF wall detector of the food experiment.
Thank you. Perfetto. Thank you. So, FOOT is the acronym for fragmentation of target, and is an applied nuclear physics experiment that aims at measuring the fragmentation cross-section for ions and energies of interest for hadron therapy and radio protection in space. Just a bit introduction for the motivation of this experiment. One of the main advantages of hadron therapy is that the dose is mainly released on a well-defined depth that is named Bragg peak, as you know. But if we look at the depth dose profile and we compare the measured one to the one that we expect, considering just the primary particles, we see difference in the not negligible difference. This difference in the entrance region are due to target fragmentation, tissue fragmentation, that cause the generation of ions in the entrance channel with a very low range, few micrometers usually, but with a high RB, with a high effectiveness. And if we consider a projectile with charge higher than proton, we can have also projectile fragmentation that causes the generation of ion that go beyond the position of the Bragg peak that we want to avoid, because here usually there is healthy tissue that needs to be preserved. So a full knowledge of differential and double differential cross-section needed to be known in order to put this information in the treatment planning, but up to now are still missing. So another application, as I told you, was radio protection in space. Astronauts, as you know, are subjected to different radiation sources, solar particle event, galactic cosmic rays, or geomagnetically trapped particles. And if you look at the spectrum of galactic cosmic rays, we saw that they are mainly protons, but there is also heavier ion from helium down to irons also. And the energy distribution is mainly peak around 700, 800 MeV. So this particle flux correspond to about 1 millisievert per day. That is absolutely not a negligible amount of dose. If we consider long mission like mission to Mars or Marconi, and these need to be taken into account also.
So also in this context, the knowledge of the fragmentation cross-section are important for a radio protection point of view and also for an optimal study of the shielding of the spacecraft. To summarize the measurement that Foot aimed to perform regard the Proton from 200 MeV up to 800 MeV, impinging on the target that are the mainly constituent of the human tissue, that are carbon and oxygen mainly, and the carbon for carbon therapy application that are impinging on carbon, proton, and oxygen. So in case of target fragmentation, the fragment has a very low path, so how we can track these, we can study this kind of fragmentation. We work in using an inverse kinematic approach. So we are using carbon or oxygen ion impinging on the proton target, I mean a hydrogen-enriched target, and then we obtain the cross-section that we are that we need. So this is the electronic setup that we are using. This is composed of a upstream region which with a star counter detector used for the first timestamp of the time of flight, and beam monitoring used to track the direction of the incoming particles. Then we have a target and a tracking region that is composed by pixelated detector and 2 magnets and silicon strip detector here. And then we have a downstream region composed by a top wall detector and a BGO calorimeter that measure the kinetic energy of the fragment. The angular acceptance of the system is about 10 degrees, and the system is mainly focused on heavier ion or fragment with a charge greater than 2. For lighter fragment, a different setup is foreseen. The system works at about 1 kilohertz acquisition event rate, and is, as you can see, is quite compact, about 2 meters, something more, because it needs to be used in different accelerator facilities, so to have access to different beam and different energies. So to focus on the TOF apparatus, we have a star counter that gives the first timestamp for the time of flight measurement, and it is composed of a plastic scintillator layer as thin as possible because it's before the target. It's 250 micrometer thick, and it's read out by 8 group of silicon photomultipliers. And then there is a top wall detector in which I'm focusing on this presentation, that is composed of plastic scintillator bars, 2 layers of plastic scintillator bars arranged orthogonally. This second detector measures not only the second timestamp for the time of flight, but also the energy released on the bar, and so the dA over the X information, and then we can, using these 2 detectors, we can reconstruct the charge of each fragment. The top wall detector has an active area of 40 by 40 centimeters square. It is composed by 20 plus 20 scintillating bar with a thickness of 3 millimeter. At the end of each bar, we have 4 silicon photomultipliers arranged as the parallel of the 2 series of 2 SIPMs each. And the cell size of the SIPM is 25 micrometers, so to have to collect a large amount of photon. And here you can see a picture of the detector. The data acquisition system is based on the WaveDAC system that digitize the signal of each channel of the top wall and of the star counter that are triggered. And this signal, after that has been digitized, were stored and then were post-processed. So to obtain a timestamp and a value of charge for each end of the 2 bars that were triggered. and a timestamp for the star counter. Then these information were combined together to obtain the time of flight for each fragment. You can find more information about the wave duct system on the poster of Stefan Ritt, more information about the trigger of the foot experiment on the poster of Luca Galli. So these are the what we want to what we aim to measure. We want to assess the time and the energy resolution of the top wall detector, to check the uniformity of response of the detector, and also the capability to reconstruct the atomic number of the ion that are used. To do that, we took data in 2 different accelerator facilities using proton, carbon, and oxygen beams with different energies. And we have a system that allows to scan the detector, to move the detector, so to irradiate a different bar in different positions, to have a full characterization of the detector. I started with the results concerning the time resolution. We plot here the time resolution of one layer of the top wall detector respect to the other layer of the top wall. And the scale is picosecond, of course, sorry. And you can see that between the 2 layers, we obtain a time resolution of 150 picosecond for proton with 60 MeV of energy, and a time resolution between 50 and 35 picosecond for carbon ions from 400 MeV per nucleon to 100 MeV per nucleons, and also for, we tested also for oxygen ions. And we reported also here the overall resolution of the TOF system, which is 74 picosecond for 400 MeV carbon ions, and which is 51 picosecond for 400 MeV oxygen ion. And as you can see, here we show the TOF response as a function of the position that the ions is interact along the bar, and you see that the response is quite uniform, at least within the resolution of the detector. And the resolution plotted here, of course, is twice the resolution of the top wall, since the timestamp of the top wall detector is obtained as the average of the timestamp of the 2 layers. So we checked also the uniformity in the resolution of the TOF detector. To do that, we scanned the detector moving continuously the detector and keeping the beam, impinging the beam on all the possible intersection of the bars. And as you can see, the resolution is quite uniform between 50 and 60 picosecond. Here we plot the resolution between the star countered and each of the 2 layers separately. So only one of the 2 layers has been considered in each one of these 2 plots. And there is a few missing points just because the detector was moving continuously and the beam has its own duty cycle, so sometimes some position was missed. So we investigate also the capability to determine the interaction position on the detector. Of course, if we have just one ions, it's straightforward, since there is just one bar on each layer that is triggered. But if we have more than one ion, we need to disambiguate all the possible intersection between the bars. We can use the information of the other detector, but we verified here that the TOF wall alone can disambiguate these multiple events
comparing the timing, timestamps that are collected on the two sides of the bar. As you can see, the time difference between the left and the right side of the bar depend on the interaction position of the fragment. There is a clear linear dependence. And so we obtain also the spatial resolution on the bar as a function of the energy released on the bar. The energy released has been evaluated using a Monte Carlo simulation. And so we have 4 centimeters spatial resolution for proton and close to 1 centimeter spatial resolution for carbon ions. And the contribution of the full width of max of the beam has been already subtracted in this plot. We performed also the energy calibration of the detector using the energy released, evaluated using a Monte Carlo simulation and fitting the collected charge as a function of this energy using the Birk's equation. And we obtained a calibration for each bar of the detector. We plot here the results for one bar as a function of the interaction position. As you can see, the K parameter is quite uniform, as we expect, since it's depend on the material, not on the position, while the collected light depends on the position. So these need to be taken into account into the calibration process. And inverting the Birk's equation, we can obtain also the energy resolution for the detector. And the energy resolution, considering both the layer of the detector, is about between 5 and 5.5% for proton, while it's between 5 and 4% for carbon ion, depending on the energy of the particle. After all this calibration, we can, by inverting the Bethe-Bloch equation, we can reconstruct the charge of the fragment. And you can see here an example of the reconstructed, the Z reconstructed during an irradiation with oxygen ion of a graphite target performed at the GSI facility. And we obtained a resolution of 2.7% for oxygen ion and 3.9% for carbon ion, both at 400 MeV. So in conclusion, we measured the time resolution and the energy resolution of the top wall detector for the foot experiment. We obtained a time resolution in the range of 50-35 picoseconds between the two layers for carbon ion, then an energy resolution between 4 and 5%. We obtained an overall time resolution between of 51 picoseconds for the TOF of the foot experiment for oxygen ion and of 74 picoseconds for carbon ion. And we obtained a resolution in the charge, in the reconstructed charge, between 3 and 4% for oxygen and carbon ion. Thank you.
Okay, thank you for the presentation. Time for questions.
You're determining the timing resolutions and the energy resolutions from the waveforms you get from the bars, right? So what algorithms do you using there? You use digital concentration discrimination, or what kind of things you use there?
Yeah, for the time resolution, we use a constant function discrimination at the 30% of the level of the
And that's the optimum
waveform.
that you figured out.
Yeah, that was the optimum.
And for the energy
the waveform was digitized at 3 gigasamples per second.
Yeah.
So we have the full waveform to analyze.
And for the energy resolution, you also do some baseline subtraction before the peak to get rid of low frequency noise and stuff like that.
Yeah, we do a baseline subtraction, and then we evaluate the area of the waveform. But then we have to calibrate to take into account the charge collected as a function of the position in the bar, and then to convert the Birk's equation.
Yeah. Okay, thank you.
Okay, I don't see any more questions. So let's thank the speaker again and move on. Okay, now our next speaker is Jean-François Prout, and he will talk about the photo detection module technologies for particle physics and medical imaging. Please start.
Thank you very much. It's a pleasure to be here, and thanks for taking the time to be here instead of the beach. I appreciate. We're developing photo detection module for a new experiment in many fields, and today I'll put the focus on the particle physics and astrophysics. But before I go in presenting the different aspect of this detection module, I think it's important to understand why, what is our motivation to do so. So PMTs have been used for many decades, and they will still be used for years. That said, Noble Liquid experiment, they want to improve the sensitivity to actually increase the discovery potential. And to that end, well, PMTs are about 1,000 times more radioactive than any other silicon-based sensor. So we need to find a new solution. And for instance, analogous IPM is one that is being used right now. So, and it also in recent experiment, for instance, Nexo and also DarkSide, the electronics and the photosensor are either located near or inside the Noble Liquid. And that puts some stringent requirement. For instance, you have to match the coefficient of thermal expansion of all the components you want to put in there, because you want to be able to assemble at room temperature, you want to be able to test at room temperature, and then operate at cryogenic, and you want everything to stay sturdy and not break apart. Second, you also, like I mentioned earlier, you want to keep the radioactive background low to achieve high sensitivity, and the power consumption must also be kept low in order to avoid boiling or convection of the Noble Liquid. So, analogous IPM is now the new trend for neutrino, dark matter, and neutron imaging. We see them all over. But there's a next generation sensor that we call Digital S Ipm. It's I would not say, I think it's just an improvement, the big brother of the analogous IPM. And so some people call it the Digital S Ipm, and the way we like to call them is photon to digital converter, if we make an analogy with the analog to digital converter, because basically what it really does is take photon and convert it to digital bit. So as I want everyone to be on the same wavelength with me, let's take a few minutes to make sure we understand what's the difference between an analog and a digital SIPM. So actually in both cases, they use SPADs, single photon avalanche diode. In the analog SIPM, you're going to have a resistor to quench the SPAD. Whereas in the digital one, with the photon to digital converter, you're going to have a quenching circuit, which is made of a CMOS electronic circuit. With the analog SIPM, you have all the charge being summed in one node, and then you're going to use a preamplifier to convert these charge into voltage. Then you're going to shape them with a shaper, and you're going to then use an analog to digital converter to bring this back to the digital world. Whereas with the PDCs, you already have photon to bit conversion at the sensor level. So with using digital signal processing, you don't have to go the old detour of going to the analog world and most likely save some power. So now let's look at some advantages that actually motivate the work of developing new photo detection module. So with analog and SIPM, if you want to cover large area, you're going to put series and parallel combination of these sensors to cover larger area. And that means that, actually in the previous slide right here, you're going to end up having to deal with a huge capacitance here at the input. And for those of you that are familiar with electronic design, front-end electronic design, that capacitance has a direct impact on noise. That means it has a direct impact on your single photon resolution. And to beat it, you need to increase the power you're going to put in the analog front-end. In comparison with photon to digital converter, capacitance is no more an issue because you read out each individual SPAD. You don't have to sum all of them with a big node of capacitance. And you can basically do photon counting on the overall dynamic range, which you cannot do with an analog SIPM because of the charge fluctuation from one SPAD to another. Another major advantage. Now, if you look on the bottom left plot here, with the analog SIPM, due to that large input capacitance, if you put them in series and parallel, you're going to end up slewing the input signal, the rising edge of the scintillating signal. If that orange line right now would be the scintillating response, you're going to be slewing the rising and also the decay of it. So you basically lose the shape. So if you want to do pulse shape discrimination, for instance, nuclear recoil with electron recoil, or with neutron imaging, for instance, we can take gamma to neutron difference. So you want to do pulse shape discrimination, where, well, with digital SIPM, you can just bin and count this scintillation light, and then pulse shape discrimination becomes trivial with digital signal processing. Another point regarding dark count. It is well known now in the literature that about 90% of the dark count are due to the 10 noisier SPAD of the array. With an analog SIPM, you can't do nothing about it. With a digital SIPM, I can just shut them off. And then I can win significantly on the noise. And I will show you measurement about this in the next few slides. Also, regarding this impact, this morning there were people discussing about the radiation damage. Now, it has nothing to do with particle, it's a parenthesis, okay? It has nothing to do with particle physics, but for energy physics, that have to deal with radiation hardness. In our case, if you have a noisy SPAD with analog SIPM, if you have noisy SPADs, you're going to increase your noise floor. You lose single photon resolution until, for instance, like it was presented this morning, you do that thermal annealing to recover some SPAD. In our case, you could do the same thing, but in the meantime, you can just shut off the noisier one, and you can still keep your single photon resolution. That could be an asset. The only impact is that you're going to lose some of the counts at the higher end of the dynamic range, which most of the time is not an issue. Now, coming back to my talk, regarding the cryogenic operation, after pulsing increase as you go lower in temperature. With analog SIPM, there's nothing you can do about it, but that said, I will give the manufacturer the credit that they've been lowering this impact significantly recently. That said, with PDC, we can control the time we keep each of these SPADs off. And by doing so, we can lower dramatically the impact of after pulsing. So this is it. This is the photo detection module we've been working on for years, and that we have also collaborator now joining and working with us. On top, we have the PDCs, the photon to digital converter, where we have the SPAD array in 3D bonded to the CMOS electronics. Then this goes to a silicon interposer that acts like a printed circuit board, which provide mechanical stability because everything is made of silicon, so we match coefficient of thermal expansion. Power management unit to regulate all the power for the system. The TAL controller, which is the brain of the system, sends the clock to every chip, gather the data. And then we have here what we call a photonic engine, which is composed of a CMOS driver and a silicon photonic chip technology, where the goal is to send data out using optical fiber to the acquisition system directly and not use copper. So now let's look into the SPAD. So actually in the world premiere today, I'm very happy, and with my colleague Frédéric Vachon, who's on the other side. Hi, Frédéric. Presenting his poster. This is the SPAD, and actually I have to tell you, we've been lying to you for the last 4 or 5 years. As you can see here, it's TSV-less. This is what I've been showing in all my talks in the last 3 years, where you see that the SPAD is read through a silicon via that brings a signal to the CMOS. The reality is not so. The reality is that these SPADs are 20 micron thick, and that we come and read out the cathode from the backside, as you can see here. Sorry if I'm shaking a bit. So here we have an aluminum germanium eutectic bonding, where I read out the cathode to the CMOS. We have trenches that go all the way through the wafer, so that basically we can have optical and electrical insulation. And then the pitch is 78 micron. The array that we are building now is 64 by 64, but there's not a limit on that. And at this phase right now, the wafer, the sensor is bonded to a mechanical wafer, so we route the signal out, and that we measure it with active probes that comes on top. But eventually, this will be replaced with CMOS, and that hopefully this will be done by end of 22, beginning of 23, whereas actually the CMOS wafer has been ordered in February. So now let's compare let's show some measurement. So this here, what I do with these two columns is that I compare the 2D device that we have developed with thick wafer, not thinned down, no bonding. And we wanted to see the impact of thinning down these wafer and putting the bonding, and for other reasons, so that here what you have is the thinned down version, the latest measurement compared to what we had in the past. So if you look at the top, we see that the breakdown voltage is slightly higher. The dark count is 0.05 count per micrometer square. And now I will come back to what I was telling you 2 slides ago, that we can control dark count. Here what you see is the population of dark count, of the dark count rate, with respect to the population of SPAD in an array. And as you can see, if in these measurements that we did on our stuff, if we shut off 10% of the SPAD, we get rid of 93% of the dark count rate. And if I want to keep more fill factor and I'm willing to sacrifice only 5% of my SPAD, I can still win 87% of my dark count, which is still significant. After pulsing is about 10 to 15%. We have a PDE above 55% at 450, and above 15% between 400 and 810. And the timing resolution, when they were not thinned down, were about 33 picosecond at 410, and now we are at 130, which is a significant degradation. We do have an impact with the fabrication when we went to 3D, when we did the final metallization, and we're investigating this. We do have some good idea of what it could be, but actually this is one of the reasons me and Frédéric are here this week, is we'd like to discuss with people that have some know-how in fabrication, and maybe we can have some more hints in ways we should look. And again, please have a look at my colleague's poster on the other side this week. Also, now let's move to the electronic, the CMOS, and the tile controller. So, the CMOS part right now, in order to develop the system, what we did is we didn't wait to have the whole thing to start doing measurements. So we developed the SPAD, the 3D bonding, and the CMOS, everything in parallel. So what you see here, eventually we will have the 3D SPAD above the CMOS, but right now, as far as the CMOS is the yellow box, we have 61 SPAD. So 61 SPAD in 2D within the same chip, so that we can test the electronic architecture. In that chip, it has 3 main outputs. We have a flag or 3, so that basically, whenever we have a pixel that fires, we get a hit, we get a flag. And that flag goes to the brain of the system that I told you earlier, the controller. And when this guy sees that there's a flag coming from a PDC, well, it can either say, okay, as soon as I have a hit, I read out everything. Or we can say, let's put some coincidence in it. Let's say I'm going to wait to have that amount of count in that amount of time, and then I will read out, start an acquisition, and this way I can get rid of even more dark count. So, and when that happens, the controller sends an acquisition signal to the chip, and then we have a digital sum. We have a 128 deep FIFO, and we send the sum out to the controller to get the signal. So what you see here in this diagram, here you have what we call the N module. On this, you have 4 chips. 4 PDCs, 2x2 array, that are interconnected to an adapter board that actually take care of the bias and transimpedance amplifier and test point. And then we have the tile controller, which for now is implemented into an FPGA board. And the reason is that we wanted to be able to play as much as we wanted with the VHDL code, so that we can learn and play with how we could operate our SPAD and our PDCs. But this will be soon to be in an ASIC. The design is started right now, and we should fab this, I would say, the end of 23. This is an acquisition that we've made with the chip with 61 SPAD. So this setup with a LED source right here, just like if I would shine it with my laser like this. And bear with me for these measurements. So the yellow curve is the LED, it is the current going through the light emitting diode. The green signal is we have an output, a test output, just to debug for debugging purposes that we call an analog monitor. And that's basically, as you can see, it respects the shape of the current pulse coming in. And here on top is the digital acquisition request from the controller saying, hey, send me data. And the beauty is that 128 deep FIFO, we can control the bin width. We can have bin down to 10 nanoseconds up to X number of clock cycle you want. And all that programmable for 128 bins, so that you can basically do pulse share discrimination the way you want. Only 3 minutes, okay. And in this case, as you can see, we have 50 bins at 10 nanoseconds and 78 bins at 110 nanoseconds. And in this case, so the total acquisition was 9 microseconds. And if you look at the digital count, really the digital bit that came out, you can see, and if we look at the dots overlaid on the analog, it's basically exactly the same shape. Now let's talk about silicon interposer. So what we want to build is an 8x8 module for the photo detection module, which would be basically roughly 5x6 millimeter. And what you can see there, this was developed with IZM Fraunhofer that we actually met here through, in Elba at the last meeting, and that's how this work got started. So thanks again for this meeting. And basically what it is, it's 2 identical wafer bonded together in the middle. So as they are identical, we match the mass, and then we avoid warping at cryogenic temperature. And it has 4 RDL, 4 routing layers. So first we have metal 1, which is responsible to interconnect the through silicon via to the back metal. And we use metal 1 and metal 2 as well for power distribution. And then we have metal 3 and metal 4 on top for transmission line using coplanar structure, as well as for signal routing. Now we have many test structure that I would skip because of time, but we wanted to test many things to make sure that we qualify the process, and we did, based on that and the measurement we developed design kits for Cadence, Mentor, and Keysight, so that we can share this with the community and hopefully maybe do some MPW based on that, multi-project wafer run, so that each of us can design his own interposer if they need. This is actually a 200 millimeter wafer process. We did some measurements, so quickly we did the sheet resistivity and the via impedance measurements. Without going into details, because lack of time, I will tell you that everything is under control to be able to develop a circuit. And we look at overlaps, we look at shorts between different metal layers to make sure that the process is sturdy. And as you can see, on a total of 7,800 measurements, we measured no short at all. So now, regarding the silicon photonic engine, as I planned, I'm lacking of time, so I will skip this, but I do have backup slide if you want to ask questions. And then I move to my conclusion. So since the last 3 years, I would say most of the modules are on the way. There is no roadblock. The SPAD optimization will start. So because the SPAD we have now are meant to work, but we still have now to improve them, improve the fill factor, improve the junction profile and all this. The CMOS wafer are ordered. The interposer, the characterization is mostly done, and we're going to start designing the circuit for the analog version of Nexo, the baseline version of Nexo, and for the PDC version. The controller, FPGA, is also to start soon, and the silicon photonic is on the way. We have 3 chips already built in silicon photonic technology. And I'm looking for partners. So if people in this crowd are interested in designing the power management ASIC for the system, come and see me. We're looking for partners. We cannot take care of everything, and we need people on that. Regarding the CMOS, we still need to rely on wire bonds, and that's a loss of fill factor and then enhance photosensitivity. So we want to put TSVs in the back, just like they did with the TimePix chips. So if you want to work with us to take care of that part, it's all yours. And we're also looking for people who want to learn how to handle these systems, make bigger system out of it, the mechanical and all that, so that we can make large system out of it. And also looking all the time for ideas and collaborator. I want this to be open science, and not something like a small niche somewhere. And looking for postdoc and PhDs, so if you got inspired by this, come and see us. We can discuss if you want to come for a few years in Quebec. It's pretty nice and not as hot, but it's beautiful too. And looking in partner who wants this technology, and again, please visit my colleague, Frédéric Poster. Thank you very much.
Thank you. Way back.
See someone back there?
Yes, yes. There is a mic.
I have a question regarding slide 16.
Yes, sir. Yep.
There you have two silicon vias at the depth of 300 micron, which I consider quite challenging. And what is the aspect ratio of the silicon vias? And are you already having samples, or is this a wish?
No, this is not a wish. I believe it's 10-to-1 or 8-to-1. I would have to check with my grad student who's leading this, but I believe it's 8 or 10-to-1. And this is a real wafer. This is not a drawing. This is a picture of a 200 millimeter wafer. And we have this full stack up in the lab right now on which we made this measurement that you see here.
And the pitch of the TSVs is how much?
The
pitch.
Oh, the pitch. I don't remember that. Let's see if I have it in my backup slide.
Okay, I mean, my real question is, I mean,
no.
At least until very few years ago, TSVs with 300 micron silicon thickness were quite challenging, to say the least. So you're saying this is now routinely done, 300 micron, you don't need to thin the silicon, nothing?
You can talk with IZM Fraunhofer.
I know IZM, yeah.
IZM, and we work with them on this.
Okay.
So they were the expert on the fab side of this device. We didn't develop the process. We told them what we wanted. We worked together on that. We did the characterization. They developed and fabricated the wafer in Germany.
Okay, thank you.
My pleasure.
Can you please comment something else on the fill factor, on the fill factor you are achieving now, or what you expect to achieve, because you were talking about that.
It's not going to be very high. If you think about each of these chips, each of these gray chips are 5.3 by 5.85 millimeter with an active area of 5 by 5 millimeter square. And we are accounting for about, I think, something like 2 millimeter between rows for wire bonding. So I don't have the final number in my head right now. I can get that to you. I know we also have this number somewhere. But yes, no, and that's why I want to put TSVs in the CMOS so we can get rid of all these wire bond and make it way tighter. Yes. No, it's part. Again, we're developing technologies. We're having fun doing these things, and the goal is to make things work, to develop them, gather the people to work on this and have interest, and then funding comes in from everywhere, and then we can improve. That's my sales pitch.
Okay, thank you.
Hi, it's a very impressive development. However, when people have talked about this in the past, there was a problem, and that is that there are fundamental patents held on digital readout of SIPMs by some companies.
Yep.
How did you get around that?
We've been studying very carefully all these patents, and first it's science. I'm not selling anything, so I'm allowed to do all this. So far so good to my understanding.
Okay.
Yes.
Best of luck.
Best of luck, thanks.
Okay, if there are no more questions, then thank the speaker again.
Thank you.
Our next speaker is Roberto Di Napoli, and he will talk about Okay, he will talk about the item 3, a high-performance single-photon counting strip detector.
Yeah, the correct name is unfortunately Mythen 3. No, sorry, it's a joke. It's a joke because it's a German thing. I always fight against German's name, but I never win. So, as I said, as he said, we are going to show you single photon counting strip detectors. So the first question is, why a strip detector? Well, first of all, in photon science, this is where we are developing chips, several applications do not really require a 2D detector, but they are 1D is enough. So for example, X-ray powder diffraction, XRPD. And then there are a big number of reasons which all boil down somehow to the point that everything is easier, cheaper, and faster in strip detectors. So this means that they are also the best playground for new ideas that then can be spinned off to pixels if they work. Additionally, the fact that they are not so fancy or not so interesting maybe means that there are really not a lot of good chips around. And we also wanted to update our ASIC. So the project, the Mythen project, started in 2001 with Mythen 1, went on with in 2007 with Mythen 2, and already with these two chips we had a huge impact in 1D photon science, and in particular XRPD. The new system, which is called Mythen 3, again for power diffraction mostly, it's based on the module. This is the readout electronics, and here we have the sensor, which is 1,280 strips with a pitch of 20 microns. And this is served by 10 readout chips. This is what we are going to see during this talk. And the modules are arranged in 2 rows to cover the gaps. And then you can put them in this configuration to cover 120 degrees at the same time. So the design specifications, well, we wanted to improve with respect to the old chip, which was in 250 nanometer technology. Now we are in 110 nanometers. We wanted a noise of about 150 electrons to be able to, and a minimum threshold of 3.5 kV to be able to access lower energies and to have better fluorescence suppression. A threshold dispersion of about 15 electrons for a better flat field. In particular, we were aiming to higher count rate capabilities. So at 90%, we wanted to go to something like 2.5 mega counts per second per strips to be able to accept a higher photon flux. We wanted to go to a frame rate of more than 10 kilohertz and dead time free readout to be able to do time resolved experiments, to keep under control the temperature instabilities, to have double polarity, to be able to use also other materials like high Z or LGATs. And also we wanted more counting, more counters and more specific logic to enable newer operational modes, and also this means new applications. So the basic of the channel is this. We have a front end with a preamplifier and a shaper, and we can tune the gain and the timing and the noise of these two. And then we have 3 comparators in parallel. The 3 comparators are completely independent, so every one has its own threshold. And on top of that, every single comparator of every single strip has 6 trim bits to reduce the threshold dispersion. The comparators go to a counting logic, which then increments 1 or 2 or 3 of these counters, which are 24 bits, and then these are read out with a control and read out logic. If you see something violet, I have backup material available, you can ask during question time. So the chip has really many different modes of operation, but some of them I'm not going to describe because they're kind of trivial. The 5th is actually extremely interesting. It's an improved performance in pulse mode, but we have not tested yet, so I'm not going to describe it. But I'm going to go through all this mode of operation one after the other. First of all, very quickly about chip performance. Thanks to our 6 trim bits, we managed to reduce the threshold dispersion, which is about 123 electrons untrimmed, to 6 electrons after trimming. And also for the temperature stability, we managed to measure 0.2% changing gain for every degree, which we find acceptable in our working condition. So the basic operation is one counter, one comparator. This is still interesting because you can go very fast. For example, if you read only 8 bits in that time-free mode, you can have 400 kilohertz frame rate, more or less, and this enables time-resolved experiments. So yeah, we have tested it and it works. Another quite typical thing is energy windowing. I guess the batteries are going low. Energy windowing, where we have 3 comparators, each one with its own threshold, and every one is connected to a single counter. So in this way, you practically slice the incoming energy of the photons, and you can detect in which of these slices the photon is. And this enables, for example, selection of characteristic line of a material, or remove the higher harmonics in synchrotron radiation. So we have tested it. This also works. I'm going to go a bit more in detail with this pump probe configuration. The architecture is one single comparator is used, but with 3 counters in parallel and 3 different enables. So you can enable at different moment in time. Of course, you need a quite good timing control of the gate signals in the order of 10, maximum 15 nanoseconds, something like that, depending on depending on experiment. So first, you can do spectroscopic measurements up to 3 temporal counting slots. And then you can do pumped and unpumped measurements with an isolated bunch. And the idea is the following. So this is how the photons arrive in time to your detector. All this gray stuff is useless. You only want to be able to detect what is happening in the middle of this gap with this single pulse. So your detector has to be able to gate this pulse and remove everything else. In this case, we then take the so-called unpumped measurements. The more interesting one is the pumped measurements, which happens in another gap, where before the probing of the sample, you have an excitation of it, which is usually done with the laser. And the time phase between the two, it can be extremely well characterized. So that's why you have a pumped image and unpumped image. We have some very preliminary results. I'm sorry, I have a lot of things which is very preliminary, and very preliminary means last week we have taken data with this. However, what you can see is that indeed here you can see that we are able to catch the single bunch in the gap, and this is done with a gate which is 10 nanoseconds long. Another mode of operation is time over threshold with internal oscillator. So this is also available in other ASICs. If one comparator goes above threshold, then it starts a counter. And this counter starts a clock, sorry. And this clock goes into this counter, and it checks how many clock cycles have elapsed. So you can see it here very, let's say roughly. You have a single normal photon, which lasts for 5 clock cycles. If you have a second photon arriving too close in time, they pile up. And so what you do is you count now 10 clock cycles, very roughly, and then you can say, okay, these are 2 photons and not a single one. And this means that you can improve a lot the count rate capabilities of the chip. This can also be done not only internally, but also with an external clock, on enable, and we had tested this already with Mutant 2, and you can see that the efficiency, that means the number of photons that you have detected over the number of photons that you should have detected, it starts at 100% at low frequency, and then it goes down. But with this mode of operation, you can really extend the bandwidth of the system. However, this works, but we didn't really characterize it because we prefer this other mode of improving the rate capability, which is pile-up tracking with 3 counters. So we have our 3 counters, same configuration as in energy windowing. This means that you have your 3 thresholds and your 3 counters there. And the idea is the following. If you have a single pulse arriving, well, you have your normal threshold, 50%, you count 1. If you have a second pulse arriving, it piles up with a single threshold. You cannot do anything, but you have another threshold. So this means that here you can say, well, we have a second photon, and you can even detect the third one with a third threshold. Here you can see a simulation of what happens with 1 counter. So that's a counter in 1 counter, in the second and in the third counter. When you put everything together, you end up with this green curve, which is actually extending the rate capability of the chip, of the system with respect to a single counter. You can model all this with an extended variation of the parallelizable counter model and extract a dead time for 1, 2, or 3 detectors. And then if you compare this with reality, well, you can see that our measurements, they match pretty well what happens in our simulations. And to put this then in numbers, well, we can see that the chip has different modes of operation. Slow minimizes the noise, and fast maximizes the speed. So you can go from 1.3 megahertz, 1 counter, to 7.4 megahertz with 3 counters. And in fast mode, you can even go to 21 megahertz. If we have a look at this plot, which is average noise versus dead time, well, you want minimum dead time and minimum noise, so this region here. Well, you can see that even for something like 5 nanoseconds dead time, you have a noise which is not dramatic, in the order of 250 electrons. But if you want to go slower, like 85 nanoseconds, you are about 140. And if you go even slower and optimize a bit better the chip, you can end up with 110 electrons RMS. So this works and meets the requirement for our future synchrotron, which is the SLS2. Another interesting mode of operation is the interpolation mode. So we want to do interpolation, but only in a digital way. The idea is that we want to make use of charge sharing to improve the resolution of the chip with respect to a single strip, to the pitch of a single strip. And the idea is that you have 2 counters, 2 comparators in this case. In this case, one detects a high threshold one, which is set at something like 50% of the incoming energy of the photons, and the other one, which is actually low, and it's there to detect if something at all is arriving into that channel. And usually this is set above noise, okay, minimizing, however, the dark counts. You still don't want dark counts there. So what happens then? That the information of this comparator is sent also to the neighboring strips. So if we have a central heat there, in this case you have a big heat here, and well, in the neighboring strip there is nothing. So the information coming from the other comparators is that we didn't get anything, and then the counter is really central, and we can give it to the central counter. However, if we have another type of heat, where you have most of the charge in B and a little bit on C, then in this case you will have, of course, a full heat here, crossing the high threshold, and then the information from the neighboring discriminator is that, yes, there was actually something here. So the heat must be between B and C, and then you can give the count to the right counter, and similarly you can do with the left counter. So in this way, what you do is you rebin a real strip of 50 microns into 3 sub-strips and virtual strips, and of course this gives better resolution. So we have measured that. We have made an image of a Siemens star. Of course, it's a 1D chip, so you have somehow to photocopy your Siemens star, which has a pitch at the out here of 60 microns. So what you do is you put a slit in front of your detector and Siemens star, and then you slide the Siemens star under the slit. In this way, with the steps of 25 microns of the motor for the sample, we end up measuring something like that without interpolation. So in this case, you cannot resolve the spikes of the Siemens star here in normal mode. However, if we go now to our interpolation mode with 3 counters and 3 virtual strips, all of a sudden the spikes become visible, and it's possible to to detect them. More quantitative tests are ongoing, in particular with this edge, but we still need a bit of data analysis there. So last topic is LGATs in photon science. So what we want to do is actually we want to access low energies. We are not really much interested about the timing, but about the gain that this type of detector can give. The first challenge is the quantum efficiency. So the point is that, well, as we know, the detectors are covered with some material which is not active, and which is not a problem for hard X-rays. But if you want to detect something which is less than 1 keV, then all these X-rays, or a big quantity of them, they are stopped here. So with something which is in the order of 1.4, 1.5 microns, you end up for 1 keV with 50% quantum efficiency. So if your goal is to have more than 50%, and you also want to end up being able to detect 250 EV photons, well, you have to reduce your entrance window to a thickness of 50 nanometers or something like that. We have a collaboration with FBK on this. We have produced really many different batches with different test structures. I am reporting a single result, the latest one, with one of the diodes. Is actually in inverted LGATs, not just a simple diode. We end up measuring 62% with 250 electron volts. So I have to say that we are definitely happy to be already there. Also quite surprised, positively surprised. And the other thing that we would like to do is, as I said, use the low gain avalanche detectors, which are segmented avalanche photodiode with a limited gain, like 4 to, let's say, 20, just to give a number, with no dark counts. And also, we have proven already with this type of detector to be able to increase the signal-to-noise ratio by a factor of 5. In particular, with Jungfrau, last week we were able to measure a noise of about 5 electrons. And if you are interested about this, you can have a look at the poster of Victoria Hinger in this section. So, in summary, these LGATs are really ideal for soft X-ray single photon counters. And in particular, we are testing right now inverse LGATs, where the multiplication layer is close to the entrance window. Very preliminary, also last week. So we have put LGATs on connected to mutant 3. Here you can see the normalized counts as a function of the threshold voltage after dark frame subtraction. So you do see S curves. You can really fit them and operate the detector down to something like 1000 EV. And you can even have a very rough energy calibration with that. But we need more time to study that. Mutant 3 status, the full detector is up and running. It works perfectly. First experiments ongoing. We have several modules installed as beam monitors to measure polarization, current, position. And to summarize, I would say that, well, we have worked to have all the specs not only implemented, but improved. In particular, we were able to go to 21 megahertz and have 3 counters to open up the possibility to have a lot of different modes of operation and of different applications. So with this, I would like to thank my group and our beamline scientists, and of course, all of you for being here. It's great to meet you again in person.
Thank you. It's time for questions. Sure.
With your interpolation mode, you have like one interpolation step, right? So you can kind of double the interpolation. On the other hand, you have this time over threshold where you can actually count how often you are, how many clocks you are over time. Can you combine these two so that you can interpolate not with one step, but with several steps, just by counting, a pulse and counting the pulse height in the neighboring somehow?
That's a good point. In principle, we could, but not with the present chip. So in the present chip, the two modes of operation are exclusive. You cannot do both things.
Okay, thanks.
Do we have more? I don't see, so let's thank the speaker again. And the last presentation, the review of the posters will be done online, remotely. So can you?
I am trying to share the screen, but it's not available.
Can you put the Zoom on? Ah.
Can you see my slides?
Yes.
So I will make a brief review of the poster sections presented early, and if you have opportunity to take time to go there and see. So we had, I'm not able to change here. We had a total of 16 works dedicated to development and characterization of the new photon detectors for particle physics and also for medical imaging applications. So I following here the order that we have in the index page. So the first of all, this work have been done by the dark side collaboration. The photon detector of the dark side is based on silicon photon multiplier, and they showed in this work the characterization of the silicon photon multiplier, single photon time resolution performed from a room temperature down to 40 Kelvin as a function of overvoltage. All of these measurements have been done at Gran Sasso National Laboratory team. Here, the next work is devoted to X-ray imaging detector, recorder for next generation of X-ray sources. The group is developing a new X-ray imager with the goal of continuous operation in excess of 100 kiloframes per second, single photo sensitivity at 12 keV, full of 10 kilophoton per pixel image and 100 micromegapixel pitch. The INFN, University of Siena and the University of Firenze groups study the possibility of replace the photon multiplier of a GAN camera for full body single photon emission computing tomography. They call the SPECT, with a large area silicon PM pixels, last speed. So the last speed is built by a ganging of several CPMs. A prototype with 80 ganged CPMs was built and tested. The camera was also simulated using the Giant 4 Monte Carlo simulation. The group is exploring the possibility to build in a full body camera also. The next one is dedicated to the full characterization of the gas avalanche diode. The sensors are interesting for X-ray applications for the wider band gap with respect to silicon and for the higher atomic number. The group of University of Trieste studied the effects of doing the different layers, the number of multiplication steps, and the role of the separation layer. Next work is about the characterization back-thinned CMOS imager with extended ultraviolet and soft X-rays. In this work, the adaptation of commercial back-illuminated CMOS for X-rays in the range of energies between 35 to 2000 electron volts is presented. The first measurement with the sensors showed high quantum efficiency in the range of 100 and 2000 electron volts. And the X-ray imaging capabilities have been assessed. Now we back to particle physics detectors for Cherenkov detectors. So TRIC. The TRIC detectors is developing an innovative 5D technique which promises to provide the position, time, and type of incoming particles. This technology is based on GEM, TPC with conventional aerogel proximity focusing reach in one box. In particular, the preparation and initial studies with the prototype were presented in this poster. Next one. So here the group of Pavia, they perform measurements of different types of silicon PMs and different producers of silicon PMs. They have been characterized the photomultipliers produced by Amamatsu to different types, KTEC, on semiconductors, and advanced, specifically the NUV for SP. They was able to do measurements between minus 16 and plus 16 Celsius degrees, and in addition, they performed measurements were done in liquid nitrogen temperature. So here we have a poster about the development of photodetectors based on organometal halide perovskites and the activities carried on within the Perov experiment, which is dedicated to find out whether OMHP shows avalanche multiplication. So the X-ray Observatory collaboration presents the qualification procedure for mass production of large area silicon drift detector. And here this poster will dedicate to the Abalone photon detector. This work has been done for people of the University of L'Aquila. And they performed the characterization of these new photon detectors, namely Abalone, that is a hybrid photosensor with a standard photocathode in vacuum. Electrons are focused on scintillation material here, and then the emitted photons are detected by silicon PMs. The poster showing this slide is a work of R&D for the scintillating fiber detector of the MU3E experiment. Very high detection efficiency, they reach higher than 99%, and the time resolution less than 500 picoseconds. For a minimum ionizing muon were measured. They got a good agreement with Monte Carlo simulations. The torch is a large area time of flight detector proposed for the upgrade of LHCb. A prototype is already done with 125 per 66 per 1 cubic centimeter. Fused silica radiator with 2 microchannels plate photomultiplier tubes. Was tested at CERN with 8 Jeff test beam and a single photo time resolution between 17 and 100 picoseconds was demonstrated. This is approaching the requirement of the experiment, that is around 15 picoseconds, taking into account that the complete torch model will detect about 30 photons. So this work presents the state of art of the current Jungfrau system and discuss recent improvements. The Jungfrau is a hybrid silicon pixel detector optimized for photon energy between 2 and 16 keV. Measurements results of the prototype for low energy X-ray detection were presented together with an outlook on possible combinations of Jungfrau with high zeta sensor materials to facilitate experiments with high energy X-rays. These works describe a novel imaging technique for thermal neutron using a fast optical camera. Thermal neutrons produce the tritium and alpha particle in lithium-6, which then interact in a crystal scintillator and produce flashes of light. Emitted photons are focused on a microchannel plate intensifier where the optical camera is installed. These new optical neutron imaging techniques allow remote and long-distance detection. And here we can see the development of single photon avalanche diode array is presented in this work, and the SPAD array developed by University of Sherbrooke and Teledine Dallas Semiconductor in Canada. This work is presented for the first time. The group is also working on the development of a 3D PDC photon to digital converter, where single photon avalanche diode array is vertically integrated with CMOS with a digital signal processing. And the last one is a work about the particle identification with Bell-2 spectrometer. The arch counter of the Bell-2 spectrometer was successfully operating since 2018 with a normal design luminosity. And particle identifications in the D+, minus, and D star decays meet the specification with Cal identification above around 96%. For operating arch beyond the design luminosity, the collaboration is studying replacements for the HAPD, such as a SIPM and large area picosecond photon detectors. So in summary, this poster section hosts a good number of excellent works on photon detection with applications in particle physics and medical imaging with relevant advances in photosensors development, X-ray imaging detectors, Cherenkov detectors, semiconductor detectors, detectors R&D, and experiment upgrades. Thank you.
Okay. Thank you, Anna, for this nice review. And with this, we came to the end of the session on photon detectors and particle ID. Are there any announcements? Not really. So thank you again, and thank all the contributors of the session.